Welcome to this explainer. Let's just jump right in. Today we're exploring a surprising, but honestly incredibly accurate biological metaphor. Think about it. It is so easy to look at a massive AI data center and call the processors the brain, right? The power supply is the heart, and the network cables, well, that's the circulatory system. But here's the thing. Every living organism, no matter how advanced or powerful, has to deal with what it absolutely cannot use. It has to separate nourishment from residue, keep what's valuable, and safely get rid of what's harmful. In an AI data center, it's really no different. It operates just like a living organism, complete with its very own renal system. So today, we're decoding the kidneys of the AI factory, the often overlooked world of wastewater management.
Now, while we absolutely love talking about the brilliant brains of AI compute and the sheer gigawatts of power required to run them, we often push wastewater to the absolute edge of the conversation. Mostly because, well, it kind of lacks the flash and drama of liquid cooling loops or massive energy grids. But the crucial point here is figuring out exactly how this massive machine excretes its harmful, concentrated residuals safely. Because the water that leaves a cooling tower, an equipment drain, or a cleaning process doesn't just magically vanish the second it crosses the property line. It enters a municipal treatment plant, a local watershed, or a reuse network.
So here's our roadmap for today. We'll be covering the AI factory's kidneys, chemistry over volume, the price of concentration, where it goes, the Quincy example, and finally, looking beyond simple water metrics.
Okay, Section 1. The AI factory's kidneys, separating nourishment from residue. Let's look at how water literally changes its identity the exact moment it flows into the facility's cooling towers.
It turns out the absolute golden rule of wastewater is this: separate first, treat second. Now, you've probably heard of zero trust in cybersecurity, right? Well, it applies perfectly to industrial plumbing too. You have to establish totally separate collection paths for things like cooling tower discharge, chemical cleaning solutions, and potentially contaminated stormwater. Why? Because if you mix clean condensate with high salinity reject water, that clean water inherits the exact same toxic disposal problem as the heavy brine. Mixing streams might simplify the architectural drawings, sure, but it makes treatment vastly more expensive and ecological incidents way harder to contain. An unauthenticated drain, basically a drain without a clear lineage of exactly what flows through it, is quite literally an ecological disaster waiting to happen.
Moving right along to Section 2, chemistry over volume, changing the measurement mindset. For this concept, we need to completely rethink how we measure our water impact.
Historically, we've been completely obsessed with gallons and liters, but focusing only on volume is a massive flaw. Think about it. A small stream of highly toxic dissolved solids is far worse and so much more expensive to manage than a massive stream of completely clean condensate. Wastewater is a chemistry problem way before it's a volume problem. The actual chemistry of the water, its temperature, pH, conductivity, hardness, silica levels, and those chemical additives used to prevent pipe corrosion, that dictates exactly what can happen to that water next. You simply can't judge a facility just by how little fresh water it withdraws. You have to judge it by the quality and the chemistry of the water it actually returns.
Which brings us to Section 3, the price of concentration, the metabolism of the cooling tower. Let's pop the hood and look at the metabolic pathway of the facility itself.
So as cooling towers recirculate water to reject heat, a portion of that water naturally evaporates. But the minerals, they stay right there. With every single cycle, the water gets more and more heavily concentrated with dissolved solids. To prevent the massive machinery from basically scaling up and choking on its own salts, operators have to release a controlled portion of this highly concentrated stream. In the industry, they call this blowdown. Now, it's not automatically toxic, but it is certainly not the clean source water it started out as.
Check out this stat from the Department of Energy. It really highlights the delicate balancing act these facilities face. Raising the cycle count, which means recirculating the water more times before discharging it, can save a ton of fresh water up front. Moving from 3 to 6 cycles saves about 20% on makeup water, which is the fresh water brought in to replace what evaporated. And it cuts your blowdown volume completely in half. But there is a catch. Concentrating water saves gallons, for sure, but it makes the resulting blowdown chemistry incredibly difficult to manage. It is a constant trade-off between volume and toxicity.
Section 4. Where does it go? 3 destinations, 3 accountability paths. So once the water actually leaves the kidneys, where does it end up in your community? Wastewater generally moves toward one of 3 destinations. It's either reused within an industrial loop, sent to municipal treatment at a city plant, or discharged directly into a watershed, and each one has its own super strict accountability path. Sending water to a municipal treatment plant is definitely the most common. But think about your own city's infrastructure for a second. Standard municipal plants are biological. They're amazing at removing organics and pathogens, but they do very little to remove dissolved salts. Handing off bad chemistry can actually break a city's public infrastructure, impairing their equipment or ruining the quality of their civic sludge. And that ultimately affects the whole community.
All right, Section 5, the Quincy example, expanding the facility boundary. To really ground this in reality, let's look at an amazing real-world case study.
In Quincy, Washington, the local source water was already highly mineral-rich. When that water got concentrated in Microsoft's data center cooling systems, it created this high salinity blowdown that the local municipal reclamation facility simply wasn't designed to handle at all. Microsoft and the city realized standard municipal systems would just fail under this load. So they partnered up and essentially built a custom closed-loop kidney for the entire region. They built a completely separate industrial water treatment facility, utilizing softening, ultrafiltration, and reverse osmosis, specifically just to keep those concentrated salts out of the city's standard plant. And importantly, this wasn't just a quick construction job. It required a full 30-year financial and operating agreement to maintain.
And the result? The EPA reports this specific infrastructure saves an astonishing 138 million gallons of potable groundwater every single year. 138 million. What we should really take away from this is that wastewater quality can literally dictate the architecture of an entire local water system. The boundary of the AI factory has to expand to include the local utility and the aquifer.
Finally, Section 6, Beyond Simple Water Metrics, the Practical Wastewater Agenda. How do we actually ensure AI factories adopt these practices instead of just hiding behind vanity metrics?
Well, you really have to be aware of what engineers call treatment theater. Is a facility really green if it's just, moving the problem down the road? A super popular metric like water usage effectiveness, or WE, completely ignores discharge chemistry. It only connects water consumption to IT energy. The crucial point here is that installing advanced treatments like reverse osmosis isn't some magic fix if you're just quietly exporting the toxic sludge, the heavy brine, and the massive energy costs somewhere else. Claiming zero liquid discharge absolutely does not mean your environmental burden is zero if you're just trucking difficult solid waste to a local landfill.
So, let's see how this all builds into a highly practical 90-day agenda that any organization can use right now to commission a responsible, end-to-end water story. It happens in 3 phases. Days 1 to 30, map the truth. You literally have to physically trace every source, drain, and destination to reconcile your drawings with field conditions. Days 31 to 60, target the envelope. Set strict limits for reuse, ensure total segregation of streams, and define those chemistry boundaries. Finally, days 61 to 90, prove the model. Pilot the changes, run scenarios where a destination completely fails, and validate your mass balance. The result isn't some fluffy PR claim, it's a defensible, heavily tested design basis.
Which brings us to our final thought. A facility that uses less water is certainly efficient, but an AI factory that maps every stream, governs every single chemical discharge, correctly manages every residual solid, and adapts its metabolism when the local watershed is stressed, now that facility has evolved. Answering this question separates the facilities that just ruthlessly consume resources from the ones that truly sustain the communities they live in. It is all about being a responsible organism. Thank you so much for joining this explainer. Keep learning, and I'll catch you next time.